I want to work through the way that we can figure out the energy eigenstates of the simple harmonic oscillator in quantum mechanics. And I'm going to use a technique using some weird operator methods rather than differential equations, which you could also do. But using operator methods, I've seen this credited to Dirac originally. I don't know for sure whether that's true, but whoever came up with it, it was really clever. It's a sneaky way of rewriting your operators in a clever way that makes it easy to find the energy states. And then what I want to do, I want to find what all the possible energy eigenstates are. I want to find what the energies are that go with them, and I want to find their wave functions. I want to get an idea of how to do that. And so I'm going to run through some definitions first, and then we'll see how we can use it to find those answers. The definitions, a harmonic oscillator is just kinetic energy p squared over 2m plus 1/2 kx squared, a spring potential energy. We're going to write that just for convenience as 1/2 m omega squared x squared, and that because omega for a harmonic oscillator is the angular frequency, the natural angular frequency, square root of k over m. So this is the same thing. It's just written in terms of omega, so I don't have to worry about the k around. Omega is the frequency. The omega is a quantity we're going to keep track of later anyway. It's a useful quantity. So I've got this Hamiltonian. Now here's the definition that comes out of nowhere. I wish I had the insight to come up with this. I don't, but fortunately someone did it for me. We're going to define an operator A hat to be this combination of things. The square root of m omega over 2h bar times just the x hat plus I p hat, px hat over m omega, get the units right. That's our A hat operator. And then its adjoint A dagger, x and p are both Hermitian operators, so the adjoint of A is just the complex conjugate. I goes to minus I, same deal. Weird definitions, right? But they're there. We're also going to find n hat, capital N hat, the number operator, which is A dagger A. You can see immediately, by the way, that n is going to be a Hermitian operator because its adjoint, n dagger, would just be A dagger times A double dagger, which is just A dagger A, same thing. So this is our deal. The crazy thing about this combination of things is the Hamiltonian then, the harmonic oscillator Hamiltonian, can be written as just h bar omega times A dagger A plus a half. Or in other words, h bar omega times n hat plus a half. So if we can find the eigenstates of n, those are also eigenstates of our Hamiltonian, and that gives us all the stuff we need to understand the system. So that's where we want to go. Now, not only do these two operators give me a very simple form for the Hamiltonian, but they also have the simplest commutation relation, simplest non-zero commutation relation I can imagine. The commutator of A with A dagger is 1. So A dagger minus A dagger A equals 1, the number 1. That's cool. Putting that together with the definition of n, we get these other commutators that the n hat commutator with A hat is minus A hat, and n hat commutator with A dagger is A dagger. So we've got this. We've got these commutation relations. That's all we need to build up solutions to this. To build up a complete list of solutions here. So here's our plan. I want to know what the energy eigenstates are, so that means I want to know what the eigenstates of n are. We better give them a name to begin with. So I'm going to define n hat acting on the state little n to be little n times that same state. In this definition, we're defining these to be the eigenstates of n hat. In particular, by definition, we're defining these to be the normalized eigenstates. Any multiple of little n ket is also an eigenstate, but we're choosing the normalized ones. So, given this, I want to know what possible n's work. What eigenvalues can I have? What states can I have? And so, let me look at this. Well, one thing I can do with this is to say, what is this quantity, this bracket? This is the expectation value of n hat in the state in the state n. Well, I know that this is just n times this, because n hat acting on the n ket gives me little n, a constant. I can pull that out. So this is just n. That's one way of doing it, just acting with this. But I also know this is equal to n A dagger A n, right? That's also definitely something I can do by definition. And the interesting thing there is that if I call this state, I don't know, psi, just give it a name. then this state over here is exactly what you'd have for the psi bra. This is the psi ket, and this is its corresponding bra. Remember, when you go from a ket to a bra, the operator that changes the ket n into a ket psi, its adjoint by definition is the operator that changes the bra n into the bra psi. So this is in fact psi with psi. Now you'd say, is that equal to 1? There's no guarantee this is a normalized state. But even if it's not normalized, it has to be greater than or equal to 0. So this state has to be greater than or equal to 0. So one result I have is that n is greater than or equal to 0. That's useful. That means that whatever my eigenvalues of n hat are, they're always greater than or equal to 0. That's one step. Another thing I can learn from that is that I know that means, oh, what did I want to say there? I know that means that there must be there must be some minimum number. So there must be some minimum n state. Because if there weren't a minimum, then we'd go down below 0 eventually. It might equal 0, might not equal 0, we don't know yet, but we've got that minimum. Okay, so that's one starting point. We've got this idea of limits on n. N has to be non-negative, and so there must be some lowest possible n, whatever it might be. Okay, got that. The mathematician in me is wincing a little because there could be an open interval or something, but we've got some minimum. All right, the next thing I want to do, the next direction I want to take this is I want to look at what happens when I act with one of our A and A daggers on a state n, when I have those things act, because we're going to find A and A dagger do interesting things to these eigenstates. So let me ask, what is A dagger acting on n? What's that do? Here's what I can do. What I'm going to do to get a sense of what this is, I'm going to act on this with the n hat operator to see what I find. I'm going to say that n hat acting on A dagger n, since n hat, the n operator, the number operator, is what I use to sort of figure out what state I'm in on some level. I'm going to work with my number operator acting on this, and then I'm going to use this commutation relation. This is equal to A dagger n plus A dagger acting on the state n. Right? I'm using my commutation relation here. N A dagger minus A dagger n equals A dagger. So I'm using that commutation relation. And hey, this term has the n hat acting on n. So this is equal to A dagger times n plus A dagger acting on my state n. Right? Because when this n hat goes over and hits the ket, it gives me its eigenvalue. And that means I can write this as n plus 1 A dagger n. But hey, suddenly we've got this great result, n hat acting on, again, I can just give this a name. I'll call this state, I don't know, if I call this state psi, different psi than last time, but if I call that state psi, then this state is also psi, and this says that n acting on psi equals n hat acting on psi is n plus 1 times the same state psi. That means that because those are equal, that means that A dagger acting on state n has to equal some number, a constant, I'll call it C plus, acting on state n plus 1. The A dagger operator has raised our n by 1. So we're going to call A dagger a raising operator. A dagger is a raising operator because it raises up our n by 1. I don't know what that C plus is just yet, but it turns out that you can work it out. You can work out what that C plus has to be. I guess by saying if this is psi, if I call that psi, then I can find this state, psi with psi, the thing I would use to normalize this. Psi may not be normalized, remember, because it's an operator acting on a normalized state. It might not still be normalized. It might be, I'm expecting to be a number times a normalized state. This is either c plus squared times the n plus 1 state with itself, which is just c plus squared. Right, because that's just multiply there, so I've got that. Or it's equal to psi, remember, was a dagger n, so this is n a times a dagger n. Got that? And a dagger, hang on, that is, I've got a dagger a would be n, I've got a commutation relation. I've got a and a dagger commutation relation. A dagger equals a dagger a plus 1. So this equals n with a dagger a plus 1 times n. Right? And this whole thing is my number operator. And so this is n plus 1 times n bra with n ket, or just n plus 1. So in this equation, I can make the simplest assumption about the phase of C plus. I can say that C plus is equal to the square root of n plus 1. So I've got that a dagger acting on n gives me the square root of n plus 1 times n plus 1. So I guess maybe I should write that in some nice, neat way. I can say that a dagger acting on state n equals the square root of n plus 1 times state n plus 1. By the same sort of reasoning, the same types of arguments, I can also figure out that a acting on n gives me the square root of n times n minus 1. A dagger is a raising operator, and a dagger is and a is a lowering operator. It lowers my n by 1. So I've got those operators. I've got this a dagger and this a, nicely put together. Here's the interesting part then. What would happen, now that I've got these results, now that I know that a raises my n and that a dagger raises my n and a lowers my n, I can put these two pieces together. I can put those together and say, how does this work? What happens if a acts on n minimum? If I have a act on my n minimum, whatever it is, well, that would give me some number times n minimum minus 1, right? It would give me a number times n minimum minus 1. Actually, I could figure out what that would be, square root of n minimum, but whatever it is, the problem is that in general, we shouldn't have this, right? N minimum minus 1, that would be bad. It would be very bad if that were there, because n minimum was our lowest possible state. So going to another state, a lower state, would contradict our assumption we were at the minimum n. So, okay, that means the only number that will keep this from happening is if that number is 0. So, the number equals 0. And hey, what number gives me 0? Square root of n equals 0. Square root of n. So that means that n minimum really is the 0 state. So we have a 0 state. There's no states with n less than 0. And we've got this 0 state. And in fact, you can even argue, if I had an n equals 1/2, this wouldn't work, right? If I had an n equals, or n equals 0.73 or something, then a hat acting on 0.73 would give me a negative 0.27, and that would break this. So we can't have a fractional state. The only states that can work that wouldn't eventually have lowering operators get us down to a negative number, the only states that will work are integers, so that by acting with a lowering operator enough times, eventually I hit n minimum and stop. So only integer states are allowed. So allowed. Positive integers. Integers greater than 0. So the minimum state is 0, and other states are positive integers. That's already kind of cool. So I now know what my possible n's are. Positive integers. From there, I can figure out immediately what my energies are. And that's kind of fun. Now that we've got that result, I'm going to go ahead and erase a bunch of stuff. Let me go ahead and do that so that we can then talk about what our states look like. Squeaky board, sorry. I'm just throwing everything away. Ha! That's okay. We know what we're doing. We've got some results. So we've got integer n's. Cool. So that tells me then that my Hamiltonian, that if I have my Hamiltonian acting on state n, that means that's equal to h bar omega times n plus a half acting on state n. So those are my energies. This is E sub n acting on state n. My energies are these h bar omega times n plus a half. And that's already a cool result, right? So E sub n equals, let me write it down, h bar omega times n plus a half for n equals 0, 1, 2, and so forth, non-negative integers. The cool result here is that these are evenly spaced energies, 0, 1, 2, they're evenly spaced, and that it starts at a half. The lowest energy isn't 0. Think about what that means. That tells me that I can't be in a state where I'm sitting still and where the spring is not stretched. I can't be in a state like that because if I were, I'd have 0 energy. This says the lowest energy doesn't do that. And when you think about it, that makes sense because of the uncertainty principle. We've learned before that the uncertainty in position times the uncertainty in momentum has to be greater than or equal to h bar over 2. Right? We've seen that. I'll jot that down. We know that uncertainty in position times uncertainty in momentum has to be greater than or equal to h bar over 2. That was Heisenberg's uncertainty principle applied to x and px. And what that tells me is that if I tried to say, okay, my spring really isn't moving, it has no momentum at all, then I'd take delta p down to 0, and delta x would become infinitely large. And so I'd have a large uncertainty in the x. That would mean that my spring would probably be very stretched. Similarly, if I said, oh no, the spring's not stretched, it's exactly at its equilibrium length, that would mean that my delta p would have to become very large, and that would then mean that that I had a lot of kinetic energy. I'd expect to have a lot of kinetic energy because I didn't know where that momentum was. So the balance, the best balance you can hit between delta x and delta p, will land you in the n equals 0 state, where you have 1/2 h bar omega as that ground state. So okay, I've got the list of energies of my harmonic oscillator states. What do the actual eigenfunctions look like? And again, this is a place where our weird operators can help us. And we're going to use the fact that the a hat operator eliminates the 0 state as our basis. So we know that a hat acting on the 0 state equals 0. And what I'm going to do, if I want to know what the psi of x is, what the position space state for this is, I'm going to just act with this with an x bra. Remember what this does. The x bra coming in sort of is asking a question, hey, are you at position x? And this is just telling me that this is just going to tell me what my function of x is, and I guess this is equal to 0. But in general, this is how you find our wave function, psi of x. And so, this is one thing. A times this equals 0. The other thing we could write, though, is we know what a is as an operator. We know that we could write this as this is equal to our x bra acting on this operator in the middle, the square root of m omega over 2h bar times all this stuff, x hat plus I over m omega px hat acting on state 0. So remember, I'm just going to get rid of this paren. It'll be fine. We know that this is the same as that by definition. But this form isn't as obviously 0 as that one is. And in fact, we can do some fun stuff with it. With these operators inside the x basis bra out front, we can do some stuff. This is going to be equal to the square root of m omega over 2h bar times what happens when this stuff, when an x hat operator hits my x bra. Remember, it's equal to its own adjoint. Well, it does that. Well, it's just x. That's what it is. So that's going to be times x times the x0 bracket plus, let me factor this m omega over 2h bar out, plus I over m omega. And what happens to px inside an x bra? In the position basis, px is a derivative, right? Times, and we can write that derivative in various ways. One way is to write it as h bar over I times d by dx of x with 0, x on state 0. That's just writing this out. Let me close my parentheses. That's just writing out what this does in the position basis. And this is actually kind of cool because we can do some stuff over here. I've got, let's see, the i's here are going to cancel out, and I've got a d by dx. The x with 0, I'm going to just call this psi 0 of x. This function, that's my wave function, psi 0 of x. By definition, that's what a wave function is. It's the x bra with your state ket. That's a wave function. So I now have a function, a differential equation, in fact, for psi of x, psi 0 of x. And I guess this whole thing equals 0, so I can divide through by this prefactor. That part doesn't matter anymore. And when I write it down, when I get rid of the prefactor, it equals 0. I get that x times psi 0 of x, the i's canceled, plus h bar over m omega times d psi 0 dx equals 0. I can solve this for the derivative, and you just do differential equations at this point. It's relatively straightforward, kind of straightforward, I hope. I get that d psi 0 dx equals minus m omega x over h bar times psi 0 of x. So we need some function whose derivative is equal to constants times x times itself. If we're just constants times itself, e to the x would be a good candidate, but it's not. It's got an x in it as well. That suggests an e to the x squared will work well. And in fact, we find that psi 0 of x equals, and there's a normalization step to do too here, some normalization factor times e to the minus, and let me get the factors right here, make sure I have this right, e to the minus m omega x squared over 2 h bar should be what I have. That's my function, and once I get this functional form times the arbitrary constant, any arbitrary constant will work for this equation, I want it to be a normalized state. The arbitrary constant that gives me that is m omega over pi h bar, all quantity to the 1/4 power, which is obnoxious, but it's what we're stuck with. There we go. That is psi 0 of x, my basic wave function for the ground state. And this is just a Gaussian. It's an e to the minus x squared function times some constants out front. It's a Gaussian, and the higher the energy, the higher the energy, the higher the frequency of this harmonic oscillator, the bigger omega is, so the faster this will fall off to 0, the sharper the peak will be, the taller the peak will be too. So this comes out to be a Gaussian function of x, and that's our psi 0. And then if you say, well, okay, what's the wave function for 1 then? This is x with 0. I guess psi 0 is x with 0. Then if I ask, what is psi 1 of x, which would be x with state 1, right? Well, I know how to get state 1. I know I have my raising operator. I can write this as x times a dagger 0. A dagger is my raising operator, and square root of n plus 1 is square root of 0 plus 1 is 1, so this will be the right thing. And the good news is I know what that does. I can put in my a dagger definition right here, put in that same definition, and what will I find? I guess I find that x with where have I got my square root of m omega over 2 h bar times x hat minus I over m omega px hat acting on 0 is there. And again, I can write this in derivative form. I can turn this in derivatives. This is equals the square root of m omega over 2 h bar times, what do I have? Same sort of thing as I had here. In fact, it'll be exactly the same as this, except for the minus sign in this step. It's going to be x times psi 0 of x minus h bar over m omega d psi 0 dx is what it'll come out to. It's exactly this thing. That's going to be my psi 1 of x. And I guess we can do this. We can plug through it. X times this, and then the derivative of this is going to be, I guess, the negative of x times this by definition or something. So it's going to be 2 times x times this. So, I mean, we can go through all these steps, right? When I go through and work out what I get for it once I've actually done this, I will get that it turns out to be kind of ugly because of the factors of. Do I have that right? I should have a normalization right. I'll get this m omega over 2h bar business comes in again. The way I end up writing it is, getting it right. Writing it down once you do it, 4 over pi times m omega over h bar, over h bar cubed, all to the 1/4 power. So it's what we're stuck with. That times x times e to the minus m omega x squared over 2 h bar. That's my psi 1 of x. I solve for that, and you get the idea. If I want to find psi 2 of x, I would do psi 2 of x equals x with state 2, and that would be x with, for this one, 1 over n plus 1, x with state 2, which is x with 1 over square root of 2 times a dagger times state 1, because remember, a dagger gives me a square root of n plus 1, a square root of 2 that it would act on, so I need to divide by the square root of 2. And I could do it. I'm not going to go through it here because it would take forever. And in fact, it keeps taking longer the longer we go at it. But I would get this thing. I can see what to do. I just put the same terms in the middle, take these derivatives, add these things together. I'll get something to go up there and find my state 2. And in general, we can do this same thing, right? In general, we can go up and say that in state n, we would have state n is going to be 1 over the square root of n factorial times a dagger to the n acting on state 0, whatever it is. Remember, each a dagger will give us a square root of the next n up. So when we get to state n, we will have acted on that up to state 1, 2, 3, 4, 5, so we get 1 over square root of n factorial we need to do. That's what we'll come up with eventually. This is how you can eventually construct all of those wave functions when you need them. Hopefully you don't need to do it too much. You could have gotten to all these same results using differential equations without doing any of this operator stuff at all. It would have been, in my opinion, it's a messier process. Well, maybe this is messy too. The operators are hard to get, but in my opinion, the operators have some sense to them. They mean something. As we went through, we learned about raising and lowering operators. We learned about the number operator. We learned a lot about the structure of these solutions. The differential equations method, if you use a series solution to a differential equation after factoring out the behavior at infinity or something, asymptotic behavior, if you do that kind of thing, you would get to a solution. It would work, but you would find the differential equations way, at least in my experience, I don't feel like I get as much insight into what's going on. Using these operator methods, the math in the middle also taught me about the system, more interesting things about the system, and that's why I like the operator methods better. Either way would work, but this way I can construct all the solutions when I want them, and I get this way of getting all my solutions to the harmonic oscillator. I guess I could ask, what do these look like, as a final question. I said this one's a Gaussian, so this one would look like some wave function, psi of x versus x, something like that. And comparing to the harmonic oscillator potential energy, right? Harmonic oscillator potential energy, if this is v of x, That means that once you get outside of the to where the well is where the sides are very steep, you've got this exponential damping out there, so it dies off e to the minus x squared quickly when you're in the classically not allowed region. And in the middle, it's kind of like a sine graph, kind of like what we would expect for ordinary like particle in a box type stuff. This one is basically x times e to the minus x squared. So this one would have given me psi 1 of, I guess this is psi 0 of x. Psi 1 of x, if I had graphed that, x times e to the minus x squared, well, it's got to have this x in it. It's going to be something like this. It's going to look like that. And again, it dies off to 0 once you're outside in that region farther out, you're going to die off to 0 quickly. But in the middle, we've got this wiggly stuff, kind of like a sine graph in there, you know? And you can imagine this would keep going, right? Psi 2 would have been the same sort of deal, where we would have had, what's this one? We did psi 2 of x versus x. This one would look something like that, where I've got 3 wiggles in there, because it's going to be an x squared and a constant term or something. And so I've got to get something there where it dies off quickly. That's the idea of what you'll find when you go to these higher and higher polynomials. It'll look wiggly in the middle, where you've got kinetic energy greater than potential energy, and it'll look or kinetic energy, total energy greater than potential energy. And when your total energy is less than the potential energy, it dies off quickly, as you'd expect for quantum mechanics. So it all sort of makes sense. It all fits together, and I hope that gives you a sense of how this structure works.